The hangar at Rechlin was cold that morning in early 1944, but Flugkapitän Werner Mulders barely noticed. His attention was fixed on the massive aircraft before him, an American P-47 Thunderbolt, captured intact after an emergency landing in occupied France. The fighter sat under harsh electric lights, its olive-drab paint chipped and scarred, but otherwise complete. Mulders had flown nearly every German fighter type, had tested captured Soviet and British aircraft, and thought he understood the hierarchy of air power. But as he walked slowly around this American machine, running his hand along the cool metal skin, he felt something unfamiliar, genuine uncertainty about what he was about to discover. The Thunderbolt dwarfed everything in the hangar. It was huge, absurdly huge for a single-engine fighter. The WWII powered Focke-Wulf 190 that Mulders considered the pinnacle of German radial engine design looked almost delicate beside it. The American fighter's fuselage was as wide as a small room, its cowling massive and blunt. German intelligence reports had been contradictory. Some claimed the P-47 was a mediocre fighter, heavy and unwieldy. Others reported it diving through Luftwaffe formations like a falling anvil, impossible to catch, impossible to escape. Now, standing in this freezing hangar, Mulders would learn the truth. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The German aviation establishment had built its understanding of fighter design on specific principles. Speed came from streamlining and lightweight construction. Maneuverability required small size and low wing loading. Power was important, but beyond a certain threshold, diminishing returns set in. The Daimler-Benz DB605 engine that powered the Messerschmitt 109 produced approximately 1,300 horsepower, a figure German engineers considered close to optimal for a single-engine fighter. Push much beyond that, they believed, and you simply added weight faster than you added performance. The BMW 801 radial in the FUR 190 pushed to around 1,700 horsepower in its latest variants, and even that was considered almost excessive, justified only by the radial engine's superior durability and ease of maintenance. This thinking wasn't arbitrary. It was grounded in years of careful engineering and combat experience. The Messerschmitt 109 had proven itself in Spain, in Poland, in France, and in the early years over Britain and Russia. It was light, responsive, and when properly flown, deadly. The Focke-Wulf 190, introduced in 1941, had shocked the Royal Air Force with its combination of speed, firepower, and ruggedness. German pilots had outfought numerically superior enemies for years. The Luftwaffe's technical confidence wasn't baseless arrogance, it was earned through victory. But that confidence was about to be tested in a very specific way. Because the question that morning at Rechlin wasn't whether the P-47 was a good fighter. Combat reports had already answered that, reluctantly. The question was how. German pilots reported that Thunderbolts could dive away from anything the Luftwaffe could send against them. They could absorb horrific damage and keep flying. They operated at altitudes where German fighters gasped and struggled. Most puzzling, they seemed to carry enormous fuel loads and still maintain combat performance. How could such a large, heavy aircraft do these things? Mulders received permission to remove the cowling. This was the moment of truth. German intelligence desperately wanted to understand this aircraft, and the engine was the key. Two mechanics worked with him, carefully removing the massive panels that enclosed the power plant. Even the fasteners were different American engineering, American specifications, everything unfamiliar. It took nearly an hour to expose the engine completely. When the last panel came away, Mulders stood motionless. The Pratt and Whitney R-2800 double Wasp sat before him like something from another world. It was an 18-cylinder, two-row radial engine, each cylinder machined with a precision that immediately caught his eye, but it was the sheer scale that struck him first. The engine displaced 2,800 cubic inches, nearly 46 litres. By comparison, the BMW 801 displaced just under 42 litres, and the DB 605 barely 36. The American engine was simply larger, built to dimensions that seemed almost reckless. But size alone meant nothing. German engineers knew that displacement was just one factor in power output. What mattered was how efficiently you could extract energy from that displacement, how much fuel and air you could force through the cylinders, how much heat and stress the components could withstand, how reliably it all worked under combat conditions. Mulders began a systematic examination, and with each discovery, his understanding of American engineering philosophy shifted. The supercharger was a marvel of sophisticated engineering. It was a two-stage, two-speed system, meaning it used two separate compressor stages and could shift between different gear ratios depending on altitude. This wasn't revolutionary. The concept was understood, but the execution was extraordinary. The turbine wheels were precisely balanced, the intercooling system complex and efficient, the mechanical linkages robust yet refined. This wasn't a prototype or an experimental system. This was production engineering, meant to be manufactured by the thousands. Mulders called over the other engineers. They needed to document everything, but more than that, he needed confirmation that he wasn't misunderstanding what he was seeing. The engine's rated output, according to the data plate still attached to the accessory section, was 2,000 horsepower for continuous mains 80s operation. With water injection, a system whose plumbing Mulders could now trace through the engine bay, it could reach 2,300 horsepower for emergency power. Some variants, they would later learn, pushed even higher, approaching 2,535 horsepower for short bursts, 2,000 horsepower. As a baseline, not a theoretical maximum or a test-bed achievement, but the routine, reliable output of a production engine installed in thousands of aircraft. The number seemed impossible. The BMW 801D, pride of the German radial engine program, produced approximately 1,600 horsepower under optimal conditions. The latest 801 TS variant, still in development and featuring its own sophisticated supercharging, might reach 1,900 horsepower if everything went perfectly. And here was an American engine, already in mass production, already deployed across multiple theaters, casually exceeding that. But the shock wasn't just the raw numbers. It was what those numbers implied about American engineering and manufacturing capability. The R-2800 wasn't a hand-built racer or a limited production special. Pratt and Whitney would eventually build over 125,000 of these engines. They would power not just the P-47, but the F-6F Hellcat, the F-4U Corsair, the A-26 Invader, the P-61 Black Widow, a whole family of combat aircraft. Each engine required precision machining of hundreds of components, careful assembly, rigorous testing. Each engine represented thousands of hours of skilled labor and sophisticated industrial processes. German industry in 1944 was struggling. Allied bombing had disrupted production networks. Critical materials were scarce. Skilled workers had been drafted or killed. Quality control was slipping. And yet here was evidence that American industry was producing engines of greater complexity and higher output in quantities that dwarfed anything Germany could achieve. The implications went far beyond a single aircraft or a single engine. This was a glimpse into the vast industrial machine that was arrayed against them. Mulders spent the next several hours examining every accessible component. The magnetos were robust and well sealed against moisture. The fuel injection system was sophisticated, ensuring precise mixture control across the engine's operating range. The reduction gearbox that connected the engine to the propeller was a masterpiece of mechanical engineering, handling enormous torque loads while maintaining reliability. Even small details impressed him: the quality of the fasteners, the routing of the oil lines, the accessibility of maintenance points. This was an engine designed not just to produce power, but to do so reliably, to be maintained by ordinary mechanics under field conditions. to keep functioning even when damaged. The fuel system revealed another layer of American thinking. The P-47 carried internal fuel tanks with a total capacity of over 300 gallons, more than double what a Messerschmitt 109 carried. With external drop tanks, which were becoming standard equipment, a Thunderbolt could carry over 450 gallons. Even with that enormous thirsty engine, the aircraft had combat radius that exceeded most German fighters by a wide margin. American pilots could fly deep into Germany, fight, and return home. German pilots, by contrast, were increasingly restricted to defensive operations within range of their bases. But perhaps most revealing was something Mulders almost missed. On the engine's data plate, along with the technical specifications, was a production date and a serial number. This particular R-2800 had been manufactured in July of 1943. It was now early 1944, and this engine had already seen months of combat use before the aircraft's capture. Despite hard service, despite exposure to combat damage and field maintenance, the engine showed remarkably little wear. The cylinder walls, when inspected with a borescope, were smooth and evenly worn. The valve train showed proper adjustment. The bearings, when the engine was partially disassembled over the following days, revealed only normal operational wear. This wasn't just a powerful engine, it was a durable one, engineered to last. German engines, by contrast, were increasingly fragile. The Daimler-Benz DB 605 required careful maintenance and still suffered frequent failures. New engines coming from the factories showed declining quality, with rough castings and imprecise machining. Combat life between major overhauls was dropping. Pilots learned to baby their engines, to avoid full throttle except in emergencies, to nurse damaged aircraft home rather than risk a forced landing. The contrast with American engineering philosophy was stark. Over the days that followed, Mulders and his team conducted ground runs of the captured engine. They wanted to hear it, to feel it, to understand its characteristics. When the R-2800 first roared to life, the sound was overwhelming, a deep, throaty bellow that made the hangar walls shake. At idle, the engine's exhaust crackled and popped, each cylinder firing with mechanical precision. As Mulders advanced the throttle, the sound built to a sustained roar, thousands of controlled explosions per second, creating continuous thrust. The propeller became a disk of blurred motion, pulling enormous volumes of air through its circle. They ran the engine through its power range, checking manifold pressure, oil temperature, cylinder head temperature. Everything functioned exactly as designed. The supercharger engaged smoothly when they tested the high-altitude gear settings. The water injection system, when activated, produced a noticeable surge in power, the engine's note deepening as additional horsepower flooded through the cylinders. This was the sound that American pilots heard every time they engaged German fighters. This was the power that allowed them to dictate the terms of combat. When Mulders finally shut down the engine after the test runs, the silence in the hangar felt oppressive. He and the other engineers stood looking at the aircraft, at this massive American machine, and contemplated what it meant. The Luftwaffe had based its tactical and strategic planning on certain assumptions about air power. Those assumptions included the belief that German aircraft were qualitatively superior to enemy designs, that German engineering excellence could compensate for numerical disadvantage, that Allied aircraft were crude but numerous. The P-47 Thunderbolt challenged every one of those assumptions. Here was an aircraft that combined brute power with sophisticated engineering, that married enormous size with genuine performance, that represented both mass production and individual quality. And this was just one type. Intelligence reports spoke of other American fighters, the P-51, Mustang with its incredible range, the twin-engine P-38 Lightning with its unique configuration. Each represented a different approach to the same problem, each backed by the same industrial might. The R-2800 examination became a classified report that circulated among Luftwaffe leadership. It made reading uncomfortable. The engine's power output alone was startling, but the report's analysis of what that implied about American industrial capacity was deeply troubling. If the Americans could produce such engines by the tens of thousands, if they could casually exceed German power output by 40% or more, if they could do this while also building bombers, transport aircraft, trainers, and maintaining a two-ocean naval war, then the material balance of the conflict was even worse than pessimistic estimates suggested. Some German engineers proposed crash programs to match or exceed American engine output, but the brutal reality was that Germany lacked the industrial capacity, the raw materials, and increasingly the time to respond effectively. Projects like the WWII and the DB603 showed promise, potentially reaching 2,000 horsepower or slightly beyond, but these remained limited production types, never achieving the reliability or the manufacturing scale of their American counterparts. The BMW 801F, intended to push toward 2,000 horsepower, faced endless delays and technical problems. By the time improved German engines reached operational units, the Americans had moved on to jet propulsion and even more powerful piston engines. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Mulders himself would continue testing captured Allied aircraft throughout 1944, each examination adding to his understanding of the technological gap. But the R-2800 remained the most psychologically significant. It represented a fundamental difference in engineering philosophy and industrial capability. German designs emphasized elegance, efficiency, doing more with less. American designs emphasized abundance, reliability, and overwhelming force. Neither approach was inherently superior in the abstract, but in the context of total war. With unlimited industrial production, the American philosophy proved devastatingly effective. The technical analysis at Rechlin was one thing. Understanding the P-47 inches, the abstract, as a collection of specifications and engineering solutions, was manageable. But for the pilots who faced Thunderbolts in combat, the experience was entirely different. The engine's power translated into tactical advantages that fundamentally altered the nature of aerial combat over Europe, and German pilots learned these lessons in the most visceral way possible through survival and loss. Oberleutnant Franz Stigler, a veteran pilot with multiple kills to his credit, encountered his first Thunderbolt formation in the spring of 1943 over the Belgian coast. He was flying a Focke-Wulf 190, at that time still considered superior to most Allied fighters. His formation had bounced a group of P-47's that were escorting B-17 bombers at around 25,000 feet. The initial pass seemed promising. Stigler's flight dove through the American formation, guns hammering, and then executed what should have been a standard escape maneuver, a steep dive to rebuild speed, then a climbing turn to reset for another attack. But the Thunderbolts followed them down. This wasn't supposed to happen. German fighters were fast in the dive, the W-190 particularly so. Allied fighters, German pilots had been taught, were slower, less aerodynamic, unable to match German diving speed. Yet here were these massive American machines staying with them, even gaining slightly. Stigler pushed his Focke-Wulf to its limits, the airspeed indicator climbing past 400 miles per hour, the aircraft shaking as it approached compressibility effects. Still, the P-47's remained in pursuit, their big radial engines pulling them through the air with relentless power. At around 10,000 feet, Stigler attempted his climbing turn. The Focke-Wulf 190 could climb well at low altitude, its powerful BMW 801 engine providing excellent low-level performance. But as Stigler hauled back on the stick, converting his diving speed into altitude, he glanced back and saw something that violated his understanding of fighter combat. The Thunderbolts were climbing with him, their massive propellers clawing for altitude, their energy state seemingly infinite. One P-47 pulled into position behind him, closer than any Allied fighter had managed before. Stigler broke hard left, then right, then dove again, desperate to shake the pursuit. Only when he reached ground level, hedge-hopping across the Belgian countryside, did the American finally break off, not because Stigler had outmaneuvered him, but because the Thunderbolt pilot had reached the limit of his escort radius and needed to return to the bomber formation. Stigler landed shaking, not from fear exactly, but from the cognitive dissonance of the encounter. Everything he had been taught about fighter combat, everything that had worked against Spitfires and Hurricanes, and even early Thunderbolts, had failed. The American fighter had more power, more speed, more endurance. It had dictated every phase of the engagement. Stigler had survived through experience and luck, not through any advantage in his aircraft. Similar stories accumulated throughout 1943 and into 1944. The P-47's power advantage manifested in multiple ways. In diving attacks, Thunderbolts could reach speeds that German fighters couldn't match without risking structural failure. The Jug, as American pilots called it, was built like a tank. Its massive airframe could withstand diving speeds that would tear apart lighter aircraft. Messerschmitt 109 pilots learned to avoid diving contests with Thunderbolts after several incidents where German fighters suffered catastrophic structural failures trying to match American diving speeds. But the power advantage wasn't just about raw speed. It was about energy management, the ability to convert between speed and altitude to maintain combat effectiveness across a wide range of conditions. The R-2800's enormous output meant that P-47 pilots could climb rapidly after diving attacks, regaining altitude that would take German fighters much longer to achieve. In swirling dogfights, this translated into a consistent energy advantage. Thunderbolt pilots could choose when to engage and when to disengage. German pilots, increasingly, could not. The psychological impact was profound. Luftwaffe pilots had entered the war with confidence bordering on arrogance. They had better training, better tactics, and they believed better aircraft. Even as the war turned against Germany, even as losses mounted and experienced pilots were killed, there remained a belief that German quality could somehow compensate for Allied quantity. The P-47, more than perhaps any other Allied aircraft, shattered that illusion. Major Heinz Baer, who would end the war as one of Germany's highest-scoring aces, later described the Thunderbolt as the most dangerous opponent in the West. This wasn't because it was the most maneuverable the Spitfire could turn tighter. It wasn't because it had the best high-altitude performance the later P-51 Mustang excelled there. It was because the P-47 combined overwhelming power with ruggedness and reliability. You could hit them, Baer recalled, see strikes all over the fuselage, see pieces fly off, and they would just keep coming. And if you made any mistake, if you let them get any advantage, that enormous engine would pull them onto you, and there was nothing you could do. The ruggedness that Baer mentioned was directly related to the engine's power. Because the R-2800 produced so much output, Republic Aviation could afford to build the P-47's airframe heavy. The Thunderbolt featured armor protection for the pilot, self-sealing fuel tanks, redundant systems, and robust construction throughout. A Messerschmitt 109 might weigh around 7,000 pounds fully loaded. A P-47 could weigh 14,000 pounds or more, nearly double. Yet because of that massive engine, it still maintained competitive performance. The weight that would have crippled a German fighter was simply muscle in a Thunderbolt. German pilots learned to respect this the hard way. There are documented cases of Thunderbolts returning to base with hundreds of bullet holes, with cylinders shot out of the radial engine, with control surfaces damaged, with hydraulics compromised and still flying, still under control. The R-2800's radial configuration meant that battle damage to one or two cylinders didn't necessarily disable the entire engine. The remaining cylinders could keep producing power, albeit at reduced levels. Multiple Thunderbolt pilots reported limping home on engines that had lost 3, 4, even 5 cylinders to combat damage. A German inline engine, hit in the cooling system or the crankcase, would seize within minutes. The American radial would keep grinding out power. This durability had a compounding psychological effect. German pilots who scored what appeared to be solid hits on Thunderbolts, who saw their tracers striking home, who watched pieces separate from the enemy aircraft, would then see that same aircraft continue fighting or successfully withdraw. It created doubt. Did I really hit him? Are my guns effective? Are we outmatched? These doubts accumulated over time, eroding the confidence that was essential for aggressive fighter tactics. By mid-1944, the Luftwaffe's situation over Western Europe had become desperate. The Allied invasion of Normandy brought overwhelming air power to bear against German forces. Thousands of Allied aircraft operated over France, and among them were hundreds of P-47 Thunderbolts. They flew bomber escort, ground attack, and fighter sweep missions. Their presence was constant, oppressive, inescapable. German fighter pilots who had survived years of combat found themselves fighting a different kind of war. It was no longer about seeking combat and winning dogfights. It was about survival, about choosing when to attack and when to hide, about managing dwindling fuel and ammunition against endless waves of enemy aircraft. The P-47's, with their enormous fuel capacity and powerful engines, could loiter over the battlefield for hours. German fighters had minutes of combat time before they needed to withdraw to refuel. The mathematical reality was brutal. The Americans could afford to lose the engagement and come back. The Germans could not. Werner Mulders, whose examination of the captured R-2800 engine had revealed so much about American capabilities, never flew combat against Thunderbolts himself. His role was technical evaluation, not frontline service, but he read the combat reports, heard the pilot testimonies, and understood what they meant. The engine he had examined in that cold hangar was not an isolated achievement. It was representative of American industrial philosophy: build it strong, build it powerful, build thousands of them. Quality through quantity, abundance creating its own superiority. The Germans tried to respond. Emergency fighter programs proliferated in the final years of the war. The Focke-Wulf TAR 152 was designed to compete at extreme altitudes. The Dornier Do 335 tried to achieve high performance through a unique push-pull twin-engine configuration. Jets like the Messerschmitt 262 promised revolutionary speed advantages. But these efforts came too late, with too little industrial support, to alter the course of the war. The Me-262, for instance, was genuinely superior to any Allied piston engine fighter in raw performance, but it was produced in only tiny numbers compared to the thousands of P-47's, P-51's, and other Allied types, and it was plagued by unreliable engines, inexperienced pilots, and Allied air superiority that made even landing and taking off deadly undertakings. The R-2800 engine, meanwhile, continued its reliable service throughout the war and beyond. In the Pacific Theater, R-2800-powered F-6F Hellcats achieved the highest kill ratio of any American fighter, dominating Japanese aircraft with the same combination of power, ruggedness, and reliability that made the P-47 so effective in Europe. F-4U Corsairs, also powered by the R-2800, became the Navy's premier fighter bomber, serving not just through World War II but through Korea and beyond. The engine's design was so sound, its engineering so robust, that variants remained in production into the 1950s and in service even longer. After the war, when Allied intelligence teams captured German aviation facilities and documents, they found extensive reports on captured Allied equipment. The analysis of the P-47 and its R-2800 engine appeared repeatedly. German engineers had understood exactly what they were facing. They had measured the power output, analyzed the manufacturing techniques, documented the engineering solutions. They knew, technically and precisely, how far behind they had fallen. But knowing and being able to respond were entirely different things. In post-war interviews, surviving Luftwaffe pilots consistently ranked the P-47 among the most feared Allied fighters. Not the most beautiful, that honor usually went to the Spitfire. Not the longest-ranged, the P-51 Mustang claimed that distinction. But the most formidable in direct combat, the most difficult to damage, the most capable of converting pilot aggression into results. The Thunderbolt's reputation was built on that massive engine, on those 2,535 horses of American engineering, on the industrial capacity to produce them by the tens of thousands. The story of the R-2800 examination at Rechlin represents a larger truth about World War II. Germany entered the war with technological confidence and real engineering achievements. German optical instruments, chemical processes, metallurgy, and many areas of applied science were world-class. But war is not won by excellence in isolation. It is won by the combination of engineering, industrial production, resource availability, and strategic vision. The United States possessed all of these advantages, and the R-2800 engine demonstrated them in concentrated form. American engineering philosophy differed fundamentally from German approaches. German engineers sought elegance, efficiency, the optimal solution to engineering problems. This produced remarkable designs: the Me-262 jet fighter, the Type XXI U-boat, various advanced weapons systems. But these designs often required precision, manufacturing, rare materials, and careful maintenance. They were engineering masterpieces, but industrial nightmares. American engineering, by contrast, prioritized manufacturability, reliability, and abundance. The R-2800 wasn't the most efficient way to extract power from fuel. It was relatively heavy for its output and consumed fuel at a prodigious rate. But it was reliable, it was producible, and it was powerful enough that these other factors didn't matter. This difference in philosophy extended beyond aircraft engines. American shipyards produced escort carriers, Liberty ships, and landing craft in quantities that seemed impossible to German planners. American factories turned out trucks, tanks, artillery pieces, small arms in endless streams. American farms fed not just American troops but Allied forces worldwide. The material abundance that German POWs witnessed upon capture, the waste, the casual attitude towards supplies, the sheer volume of everything shocked men who had fought on reduced rations and patched equipment. The examination of that single P-47 Thunderbolt at Rechlin in early 1944 provided German engineers with detailed knowledge of one American weapon system. But the real revelation wasn't technical, it was industrial and philosophical. The R-2800 engine, with its massive displacement and enormous power output, represented a fundamentally different approach to war. It was brute force engineering, backed by brute force production, wielded with brute force tactics. Against this approach, German elegance and efficiency proved insufficient. By war's end, the Luftwaffe had been destroyed not primarily by technological inferiority, though that played a role, but by attrition, by fuel shortages, by the loss of experienced pilots, by the overwhelming numerical superiority of Allied forces. The P-47 Thunderbolt contributed significantly to this destruction. It shot down thousands of German aircraft, destroyed countless ground targets, provided bomber escort that made daylight strategic bombing viable, and dominated the skies over Western Europe during the critical campaigns of 1944 and 45. The men who examined that captured P-47 at Rechlin understood all of this, or most of it, even in early 1944. They could see where the trajectory of the war was leading. The reports they wrote were factual, technical, professional, But underlying the technical language was a deeper recognition they were witnessing the material manifestation of Germany's defeat, not in a single battle or a single campaign, but in the fundamental disparity of industrial capacity between the combatants. Werner Melders survived the war and worked briefly in aviation post-war before retiring. He rarely spoke publicly about his wartime experiences, but in private conversations with fellow engineers, he would sometimes describe that morning in the hangar at Rechlin, the moment when the cowling came off the P-47 and revealed the R-2800 engine. The slow realization, as he examined each component and system, the grinding conclusion that German engineering excellence was being overwhelmed by American industrial might. It was, he said, like watching the future defeat the present. The P-47 Thunderbolt flew its last combat missions in the Korean War, more than 5 years after World War II ended. The R-2800 engine continued powering various aircraft types well into the Cold War. By then, jet engines had replaced pistons as the primary power plant for military aircraft, and the era of massive radial engines had passed. But for a crucial period in history, during the most destructive war humanity had fought, that engine, and the aircraft it powered, represented the cutting edge of air power. And for German pilots and engineers who encountered it, the R-2800 was more than just an engine. It was a revelation about the nature of the conflict they were fighting and the inevitable outcome it portended. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.